Hello everyone, welcome back to the lecture series on fundamentals of generative AI and large language models. In today's session, we will discuss about StyleGAN 2. In my previous session, we have discussed about StyleGAN, which is a variation of GAN architecture. Now there is some modification that scientists have done to StyleGAN. We will learn about that one, which is our topic of discussion today, and it is named as StyleGAN 2. So the contents for today's session goes like limitations of StyleGAN, origin of water droplet like artifacts, the architectural changes in StyleGAN 2, weight modulation and demodulation, origin of phase artifact, solution techniques for phase artifacts in StyleGAN 2, skip connection in generator and residual connection in the discriminator. So, we have seen in our previous lecture how StyleGAN works. Now, what is the need for StyleGAN 2? When StyleGAN was giving us realistic good images, generated images, what is the requirement that motivated StyleGAN 2? So, let us have a look into that one. Is there any limitation of StyleGAN for which this StyleGAN 2 came into picture? We have to look into that. So, if we see here in this picture, this is taken from the original paper where StyleGAN 2 was introduced. We will see this is a picture of a human face, and at this point it may not be visible here in the image, but if we look at the feature map, there is a kind of artifact, a kind of a water droplet kind of a thing that is present here. Similarly, for this image also, at this point there is a kind of an artifact here. So, if you see images and their feature maps, there is some kind of artifact, it is coming everywhere. Okay. So, that is one thing which the researchers found, that there is some structural thing or architectural thing in StyleGAN which is consistently giving these kind of artifacts. Okay. So, that was the reason they wanted to have a look into the architecture and change it in such a way that these artifacts can be removed. Okay. So, there are characteristic artifacts that were generated by StyleGAN. So, these are the images that were generated by StyleGAN, and there are two types of artifacts which came into people discovered. One is water droplet like artifact, another one is phase artifact. Okay. Now, we will have a look into how the architecture of StyleGAN was changed, so we do not get any of these artifacts. StyleGAN 2 was developed to remove these artifacts. That is the main reason for the StyleGAN coming into picture. The paper in which StyleGAN 2 was introduced is from the same group which introduced StyleGAN, Tero Karos and his team, and the name of the paper is Analyzing and Improving the Image Quality of StyleGAN. So, StyleGAN used to give good quality images with controlled styles, but in StyleGAN 2 these artifacts which were coming as a structural problem in StyleGAN or structural limitation in StyleGAN, that has been modified in StyleGAN 2 so that artifacts do not come into picture. So, we will have a quick review on StyleGAN 1. What was the architecture of StyleGAN 1? We know that in StyleGAN the input from the latent space, it used to go through the mapping network, and the latent space used to be a entangled latent space where all styles were entangled, and after going through the mapping network it used to get transformed into another space which is a disentangled latent space, and then that used to go through the learned affine transformation which used to give style as parameters like the scaling and the shift, and these used to go as input to the ADA in operation, and in the synthesis network the synthesis used to start from a learned tensor, constant tensor of 4 cross 4 cross 512 size, and that was the input. And when the style parameters were introduced into ADA-in, the ADA-in had two steps of operation. One is to normalize the feature maps and another one is to modulate with these style parameters. And then there was a progressive growing of the resolution. So, this block is having 4 cross 4 resolution, next block is having 8 cross 8 resolution. So, this was the architecture of the synthesis network, and we have seen that there were at every step there was some noise injection that was happening to bring in some stochastic variation in the images that are produced. Okay. So, this was the architecture of StyleGAN. Now, I have taken this image from once again the paper style based generator architecture for generative adversarial network, that is the paper where StyleGAN got introduced. Okay. Now, if we have a look into the artifacts that I was speaking about in my previous slide, these artifacts begin to appear in the resolution 64 cross 64 resolution. Before that it was not visible, but from 64 cross 64 resolution it started appearing, and it progressively increased or grown in strength as the resolutions increases. So, we have resolutions in StyleGAN till 1024 cross 1024. So, all throughout the process from 64 cross 64 to 1024 cross 1024, there was a increase in the strength of these artifacts. Okay. Now, we have to see what is the origin of these water droplet like artifacts. Okay. Now, as I was telling, in normal StyleGAN, the traditional StyleGAN that we have studied before, the ADA-in injects styles at each layer, and when ADA-in operates on a feature map, it normalizes the mean and variance of the feature map. So, this is known to us. So, it normalizes, it first normalizes and then it modulates with the style parameters that are coming from the affine transformation. But this step of normalizing the mean and variance of the feature map interfered with the signal statistics. Now, when I tell signal statistics, what exactly I mean? For any statistics in the signal, here I will mean the mean and the variance of each channel of the feature map. Okay. So, when the feature map gets normalized, the statistics, the signal statistics gets interfered. And what happens? Due to this one, there is that is the reason some artifacts come into picture. Now, why that is coming? Because mean and variance of each channel of the image, they carry the semantic information. So, they have a lot of information about the features that are present in the feature map. Now, before ADA-in's operation, the feature mean was meaningful. That means it conveyed the semantic information of the image. Similarly, the feature variance also conveyed meaningful information about the image. Now, after ADA-in's operation, what we see is this is the normalization part, and then this gets multiplied by YSI, which is the scaling parameter that comes from the affine transformation, and this is the shift parameter YBI that also comes from as a part of your output of your learned affine transformation. Now, what happens here is when ADA-in normalizes the mean and the variance, generator also learns to exploit the normalization statistics. When I tell this one, what I mean exactly is when the mean and the variance are normalized in ADA-in, what exactly they are trying to do? They are trying to remove the semantic information or the style information that is present in that feature map and then inject the new styles. Now, what is generator's work? The generator have to produce images by which it can fool the discriminator. Okay. So, in this case, generator learns how to exploit the normalization statistics. So, it knows that if I change some of the values in the mean and the variance. If I can manipulate the mean and the variance, then I can control the style in the feature map. Okay. So, that is from there the origin of water droplet like artifact come into picture. So, what happens is the generator creates one extremely large or strong localized peak in an image, okay, like a single pixel or a very tiny region that goes to a very high value, and that dominates the statistics of the entire instance normalization computes. So, what exactly I want to say here is, suppose I have a feature map with like 0, 1, 2, 7, something like this. Now, if the generator changes it like, you know, say 0, 100 to 7, the generator spikes one of these values to a very high value. Now, when I am taking the mean and the variance of this vector and compared to this one, the entire mean and the variance will be dominated by this value, correct? Because think of a class of students where all the students have got 0 to 100 marks, and one student out of all those students scored 10,000 points. Then what happens? The extreme outlier here, which is 10,000, it controls the scale at which each of the students' score belongs now. So, the mean, the variance, the everything will now will change. Okay. So, this has a dominating this becomes a dominating factor in the mean and variance calculation. So, the generator uses this trick to fool the discriminator. It spikes one of the values, and then the mean and variance gets completely determined by that one peak. So, it is entirely dependent or determined that by that one spike, and this spike manifests blob like structure or water droplet kind of artifacts, okay, in the generated images. So, when we know this change in the statistics in ADA-in is the main reason for the water droplet kind of artifacts, then what is the solution that is proposed by the researchers or the scientists? So, what scientists did is they removed ADA-in normalization completely and introduced something called as the weight modulation and demodulation. Now, what is that one? What do I mean by weight modulation and demodulation? Instead of modifying the feature maps directly, the styles now modify the convolution weights. So, we have convolution operations inside the generator network. So, in this case, in StyleGAN 2, the feature maps are not modified. What is getting modified here with the style parameter is the convolution weights. Now, how it happens? And that is called as the weight modulation. So, if we see this expression Wij prime equal to Si Wij. So, this is my original weight of the convolution matrix, and this is my modulated weight. Okay. W prime is my modulated weight, and Si is the style scaling factor that is present in the ith layer. Wij, these are the convolution weights. Okay. And Ijk, I represents the input channel, J represents the output channel, and K represents the location of the weights inside the convolution filter. Okay. So, what we are seeing in the weight modulation, what is happening? We are modulating the weights of the convolution filter, okay, instead of modifying the feature maps. And what is demodulation? In StyleGAN 2, we have weight modulation plus demodulation. So, after modulation, what happens is some channels become extremely large, okay, because we are multiplying by the factor Si, okay. So, which is the scaling parameter from scaling parameter coming from the affine transformation. Now, if some channel values become too high, what happens is this causes instability, and that to reduce that instability, we undergo the process of demodulation. What is it? That is normalize the magnitude of the weights. So, the demodulation equation goes like this: Wij double prime is equal to Wij prime divided by square root of summation over I and k Wij prime square plus epsilon. Now, we are not going into the derivation of this one. However, we need to understand what each and every term here is what each and every term here means. What is the significance of the presence of these terms? So, this is basically Wij prime, this is basically your modulated weight, and so this is basically your modulated weight, and then there is a summation over I and k. So, the summation, it adds over all input channels I and all input channels I and over all the kernel positions k, okay. And then there is a square term of Wij prime. So, Wij prime is your modulated weight. Why are we taking the square? Because if the weights are positive and negative, there is a chance of getting cancelled. So, to avoid the cancellation of positive and negative weights, this square term is taken, okay. And there is a square root. This square root restores the normalized energy back into the original scale, okay. So, that is the reason for putting the square root term, and there is a term epsilon. We know usually epsilon is a very small number which is added to avoid division by 0, okay. So, this is the equation for demodulation of the weights. And why do we demodulate them? Because during modulation it is possible that some of the channels may become very high or large in the numbers. So, in order to get rid of that one, this demodulation step is done. Now, if we have to see, let us go through the weight modulation and demodulation pipeline. So, we have the latent vector Z, then we have the mapping network that goes to the style mapping network, gives output the style vector W. This goes to the affine transformation, and we get, after affine transformation, that style parameter, the scaling parameter, it is used in the weight modulation to modulate the convolution filters weights, okay. And then convolution happens with these modulated weights, and the final feature map gets demodulated, or the weight demodulation is happening after the convolution operation happens, okay. And then there is noise injection. We all know a noise injection is done to bring in some stochastic variation in the images. So, any image that is generated, image 1 and image 2, if they are generated, they will not be exactly same, there will be some stochastic variation which is given by this noise injection, and then we get the feature map. So, this is the modulation demodulation pipeline, okay, in StyleGAN 2. Now, this is a picture once again I have taken from the original paper where StyleGAN 2 was introduced, and if we see, this is the image and this is the feature map, and we do not see any artifacts here. This is the image of a human face, this is the image of a car, this is the image of a horse or a man riding the horse, and these are the feature maps associated, but there is no artifacts that are present here, okay. So, weight modulation and demodulation, it helped to get rid of the artifacts that were coming while images were getting generated in using StyleGAN architecture. Weight modulation and demodulation was introduced in StyleGAN 2 for removing these artifacts, and here it is clearly demonstrated. Now, we come to another type of artifact which we call as the phase artifact. Now, what is that phase artifact? Let us have a look into this picture. This is the face, a human face. it is facing the camera, straight facing the camera, and you can see the teeth is aligned at with the center of the camera. Now look at the second image. Here the face gets little bit rotated, but still the center of the teeth is still aligned with the center of the camera. There usually what happens when we turn our face, the entire positions of our teeth, the nose, the eyes, they get changed, but in this case that is not happening, it is still fixed. Okay. So, here also you see there is a movement in the face's position, but still the center is aligned, the center of the teeth is aligned to the center of the camera, and so you can see there is an offset here. Okay. So, these kind of artifacts are called as phase artifacts. So, as I was telling, when the face rotates, teeth and all other features of the face should rotate, but in this case what happens is they still remains aligned to the camera's position, camera's center probably, and then suddenly jumps. Okay. So, this kind of artifact is called as phase artifact or blob, and in why it is called as phase artifact, because in signal processing phase refers to spatial alignment or positional consistency of patterns. So, any artifact that is coming into picture because of positional inconsistency, that artifact is named as phase artifact. Okay. Now, we have to look into what is the origin of this phase artifact. The main reason for this phase artifact coming into picture is the progressive growing during the training phase of StyleGAN. So, what do you mean by progressive growing? We have seen in StyleGAN that the training initially starts from 4x4 resolution, then it goes to 8x8, 16x16, 32x32, 64x64, it goes on till 1024x1024. So, this is called as the progressive growing of the resolution. Now, what happens is during the training, it starts in original StyleGAN, training begins at a very low resolution, which is 4x4. Now, 4x4 resolution, after the first layer, it gives an output, okay, and that feature map output, that intermediate resolution temporarily acts as the final output. 4x4 or 8x8 or 16x16, these are very low resolution images. They do not have enough of spatial, they do not have the ability for higher spatial resolution. But what happens here is during the training, when we are training the first layer, say 4x4 or 8x8, the layers are forced to generate very fine details too early. These fine details, the resolution does not have that capability, but still they are forced to generate the fine details, and that temporarily acts as the final output. So, whatever details that we are getting, that becomes temporarily, that acts as a final input. What I am telling will be little bit more clear when we talk about high frequency and regions and low frequency regions. So, let us have a look into this picture. Okay. So, okay. Now, here is an image of a leaf. Okay. If we see the center, suppose I take these pixel at the center, the adjacent pixel also is having similar color. So, the value change from this pixel to this pixel is not much. If there is a pixel shift, if this pixel goes here or this pixel goes here, there is a pixel shift, then it will not show up as a distortion, because the values are almost similar and the image is smooth here, the colors are smooth, small changes, one pixel shift will not distort the image. Okay. These are called as the low frequency regions. Whereas, have a look into this edge, the edge of the leaf. Now, if I look into this last tip, there is a sharp, you see this pixel, or if you take maybe a portion of this pixel and this pixel. If I shift this pixel here, the shape of the leaf will get distorted, because the pixel values here are very much different. The green value and the whitish value at the background, they are very, there is a sharp change in the pixel values. So, whenever we are coming to some sharp edge like this, say, and if I want to shift this pixel here, then what happens? The same thing shifts here. This becomes the part of the leaf, and then what happens? This entire portion gets distorted. Okay. So, these are called as the high frequency region. Okay. Now, why we are talking about this high frequency and low frequency region, we will understand in this slide. So, progressive growing causes high frequency problem. What exactly is meant by this one? Suppose we are looking during the training phase. So, the network is training at 64 cross 64. Now, why do I take 64 cross 64? If you remember, in my first or second slide, we have told the artifact starts coming visible from the 64 cross 64 resolution, and then it starts becoming stronger and stronger with the progressive growing of the resolution. Okay, progressive progressive growing of the resolution. Now, network, let us take, we are in the 64 cross 64 resolution, and the network is getting trained at 64 cross 64 okay, resolution. Then what happens here is, this layer must already create some realistic images. So, whatever be its resolution capability, still it has to create some realistic images. Okay. Now, this 64 cross 64, they do not have enough spatial precision. Maybe one pixel is covering a large image portion. So, from where it will give the finer details? It is not possible to give the finer details. Okay. Now, what happens here is, in that case, whatever details it is giving, the features become position dependent, and that is one of the main reasons for this misalignment of features as and when we go into the progressive growing phase. So, high frequency features are very sensitive to location. As I was telling, if there is one pixel shift also, there is distortion, there is flickering effects, there is inconsistency in the spatial structures, okay, as I was discussing with the leaf image. Now, if there is if the high frequency if we consider the high frequency regions, and we see that little bit of pixel shift or little bit of disalignment gives you a distorted image, that becomes a major problem in progressive growing, because in each and every step of progressive growing we expect slight misalignment, okay, misalignment of the position with respect to the previous one. Now, we will just have a look how that problem is coming here. So, we will have a small example which will give us an idea what exactly I am telling, that as we grow in the as the resolutions keep increasing, there is a problem with the alignment, spatial alignment. Suppose we have two pixels, pixel 0 and pixel 1, and the values of these two pixels, here it is under pixel 0 it is 0 and this is 1. So, basically it is the black and white. So, if we see the edge between the black and the white, we can expect it exactly at the center, exactly at the center. Okay. Now, so then we are upsampling this one. So, here instead of 2 pixels we will get 4 pixels in the same region, pixel 0, 1, 2, 3. Now, suppose the values are like this 0, 0.3, 0.6, 0.1. So, this is complete black, this is complete white, and in between there is grey portion. Okay. So, in this case, where should the edge remain? So, we have to see, in this case there is a question mark. Where will the edge be? Will the edge be here? Will the edge be here? Will the edge be here? Where exactly? Because this entire portion is grey. Yeah, there is a variation in the shade of the grey, but there is some ambiguity. So, there is ambiguity regarding the position of the edge. Okay. So, and think of the situation, here itself there is an ambiguity, it is not, it may not exactly match with the edge here. Okay. So, it may shift. If there are multiple layers of upsampling, these misalignments keep on accumulating, and at the end of 1024 cross 1024 resolution, what you get, that may be quite a bit of shift of alignment with your actual image. So, this misalignment comes with upsampling, misalignment of special features comes with upsampling, and this becomes a very important or significant problem in case of high frequency features, because these high frequency features are very much position dependent or position sensitive. Okay. So, that is the entire reason why we are getting artifacts like these phase artifacts come into picture in StyleGAN. So, we have seen that the phase artifacts come because of the progressive growing. So, what is the solution that is proposed by the researchers to overcome this problem? It is, they remove the progressive growing completely, and there are three things that they have done. One is kept the architecture fixed in StyleGAN 2, used skipped connection in the generator and residual connection in the discriminator. So, we will have a look one by one into each of them and see how they have been able to overcome this phase artifact problem. So, we will first look into keeping the architecture fixed. So, during training phase, what happens is, in original StyleGAN, in the stage 1 only 4 cross 4 resolution images are getting trained, and in stage 2 say new 8 cross 8 block is inserted, in stage 3 new 16 cross 16 block is inserted. So, every layer one new block is getting inserted. So, the architecture changes continuously, and this keeps on going till we reach the 1024 cross 1024 resolution. This is the case in original StyleGAN, whereas in StyleGAN 2 what they have done is, from the first training iteration only they have kept 4 cross 4, 8 cross 8, the entire network was fixed. So, there was no new layers that were added later. So, the architecture is fixed, that is what has been told here, keep the architecture fixed, do not keep on adding new layers in the architecture during the training phase. So, that is one of the changes that they have done in the architecture in StyleGAN 2 compared to original StyleGAN. Then what the second thing that they have done is skip connections, they have introduced skip connections in the generator. Now, what exactly happens here? In original StyleGAN generator, that is without the skip connection, we had 4 cross 4 feature maps, then it goes to 8 cross 8 feature maps, and it keeps on going till 1024 cross 1024 feature maps we get, resolution feature maps we get, and finally we get an RGB image. Okay. So, what happens here in this case is, so here it was like every feature map, every resolution had to wait to contribute to the final RGB all across all these layers. But in StyleGAN 2 what they did is, with skip connection they have done 4 cross 4 feature map when it is generated, a portion of that goes, they keep for the RGB. So, the final RGB image that is coming out, it is getting inputs from all the layers. The difference between original StyleGAN and StyleGAN 2 is, here the entire process of going through the various layers of convolution was done, and finally the RGB image was produced. Whereas in StyleGAN 2 what happens is, after 4x4 resolution processing, image processing, we get the feature map, 4x4 feature map, and portion of it is kept for 2 RGB. And similarly 8x8 feature map, a portion goes to RGB, and 16x16 feature map, a portion goes to RGB. So what happens is, your final image is getting RGB contributions from all the feature maps in, once this feature map is produced, it is getting. So what happens here is, without skip connection, the early layers have to wait through many layers to affect the output. So the early layer, this 4x4 layer, have to wait till it reaches 1024 cross 1024 to contribute to the final RGB. Okay. And what happens is, all throughout these layers of convolution, the spatial shifts get accumulated. Okay. And what happens is, this whatever comes in the final RGB, the spatial shift is already there. Whereas with skip connection, the earlier layers directly influence the final image. So a portion directly goes to the RGB, and multi-scale RGB outputs are progressively combined. So this is very, very important, because from every scale, 4x4, 8x8, 16x16, from every scale we are getting the RGB outputs which are combined together to give you the final image. Okay. So that is the concept of skip connections in the generator, and this helps in better gradient flow, improved training stability. So overall the artifact, the phase artifact can be, or the spatial shifts can be reduced, or we can get rid of that one using this skip connections in the generator. Then the third step that they have taken, scientists have taken to get out of this artifact problem, or the phase artifact problem, is residual connections in the discriminator. So skip connections in the generator and residual connections in the discriminator. So what is the core idea here? The phase shifts are basically coming from spatial misalignment or texture drifting, or the features are tied to the pixels. That is the main reason for phase shift artifacts coming into picture. So the discriminator, now this residual connections are coming in the discriminator part. So what is the function of the discriminator? The discriminator should tell the generator or force the generator to produce properly aligned image features, so that this artifact does not come into picture. Now when the progressive growing stage, or the progressive growing, is completely removed in StyleGAN 2, the discriminator is given the full resolution image from the beginning itself. Okay. So the image that is coming to the discriminator at the first instance itself is 1024 cross 1024. Now this is a large image, and the discriminator's network becomes deep in order to process this image. Now we will just have a visual representation of this. Original StyleGAN, we were having these upsamplings like this from 4 to 1024 cross 1024. So the initial part, the discriminator initially handled very small image. So this is 4x4 that is handled, and handling a small image of 4x4 resolution does not require a deep neural network, it requires a shallow network that is sufficient for it. When it comes to 1024 cross 1024, or maybe a layer above that one, the discriminator in this positions, they are handling larger images, and it requires deeper network. Okay. That was in original StyleGAN. So when progressive growing is removed, the discriminator from the initial step itself have to process the large image, which is 1x24 cross 1x24. Now processing this large image by the discriminator, it requires a lot of downsampling. Why it requires a lot of downsampling? What is the function of the discriminator? The discriminator's function is to look into the generated image and real image, and then tell which one is generated. For that one, it has to look into the features, it has to look into all the details that are present in the image. If it starts from a very high resolution one, it will be memory intensive, computational intensive. So, all throughout it cannot it will be too memory intensive calculations will be there. So, what it does is it downsamples from 1024 cross 1024 all the way down to 4 cross 4. Okay. So, each stage contains convolution layers, making the network deep in from the beginning itself. So many layers it has to process, and the problem that comes with deep network is gradient may vanish, the training may become unstable, optimization becomes difficult because it is a deep network. Now, how residual connections in the discriminator, how it helps to overcome this problem? We know residual connections work like this. So, if we have an input here x and it undergoes some convolution layers and we get an output from here, and if output from the convolutions the learned transformation is fx, then this input also comes and gets added here, and the output that we get here is fx plus x. Okay. So, what exactly we are trying to say here is whatever information is available in the first layer, let us not destroy it, let us add it with the learned transformation. Okay. So, if the original input is already having useful information which is there in our 1024 cross 1024 image, the network should not destroy it. So, the information is getting added here, and residual connection ensures the original information is added to new learned refinements without undergoing all these layers. So, directly through the residual connection, information from the first layer can get added to this layer, to the output. Without residual paths, what happened? The repeated convolutions, as we were telling before, also may distort the feature locations. So, the spatial misalignment gets added or accumulated over the multiple convolution layers that through which the image is getting processed or the feature maps are getting processed, and this weakens the initial alignment information that was there in the original feature map. So, that is how the discriminator overcomes the problem of deep network using residual connections. The generator uses skip connections, and the architecture is kept fixed in StyleGAN 2, and with these 3 steps scientists were able to come out of the or overcome the problem of phase artifacts. So, with this one I come to the conclusion of today's session. Before I conclude, let me quickly summarize what we have studied today. So, we have started with what is the need for StyleGAN 2. StyleGAN itself was giving us good realistic images, high resolution images, but it was seen that even though artifacts were not seen in the final image, but if we look into the feature maps from 64 cross 64 resolution, every feature map in the increasing progressive growth of the resolution, the artifacts were present, and there are 2 types of artifacts, water droplet kind of artifacts and phase artifacts. And we have seen what is the origin of the water droplet artifacts, what is the origin of the phase artifact, and what is the solution that has been taken for for removing the water droplet kind of artifact, and in what is the solution that has been taken in the phase artifact removal. So, we have seen in the water droplet kind of artifact, they have removed the ADA in operation completely, and it is replaced by weight modulation and demodulation, due to which the convolution weights were getting modulated and demodulated, and with this one they have been able to come out of that water droplet kind of artifact. Phase artifact comes from the misalignment of spatial features, and it becomes very prominent for high frequency features which are very sensitive to position, and the solution that was suggested by scientists were 3 things: keeping the architecture, remove progressive growing completely, keeping the architecture fixed from the beginning. So, in StyleGAN 2 we have the network fixed starting from 4x4 to 1024 x 1024, and they have introduced skip connections in generators and residual connections in discriminators. Skip connection in generators helped to solve the problem of this misalignment, of spatial misalignment, whereas the residual connection in the generator, in the discriminator, it helped to overcome the problems of a deep network in the discriminator. So, with all these things, scientists were able to overcome the problem of artifacts in highly realistic images that are produced by StyleGAN, and in StyleGAN 2 basically. And with this one I come to the end of today's session. In the next session we will discuss about diffusion models, which is another complete another topic for image generation. Okay. So, we will take up diffusion model in my next session, and till that time keep learning, happy learning, and thank you all.